Yes, one. Okay. Ágæta doktorsefni, góði gestir, andmælendur, distinguished opponents. Ég heiti Andri Steffensen, fyrir þá sem vita það ekki. Ég var að deildarforseti jarðvísindadeildar, verkfræði og náttúruvísindasviðs Háskóla Íslands og ég býð ykkur öll velkomin til þessarar athafnar. Hér mun fara fram doktorsvörn. Today, I'll switch to English now. Today a PhD defense will take place. Louise Steffensen Schmidt, who is next to me here, is going to defend her thesis. Short and long-term model simulations of the evolution of Vatnajökull ice cap Iceland. Louise's supervisor has been Dr. Guðfinna Aðalgeirsdóttir at the University of Iceland. She is sitting here in the front. And the other members of the PhD committee are Finnur Pálsson, also at the University of Iceland, Sverrir Guðmundsson at Veitur here in Iceland, Dr. Peter L. Langen, he is not here with us today, but is he on? He is here on the computer somewhere in the room. At the Danish Meteorological Institute, and Dr. Helgi Björnsson, who is sitting here next to Guðfinna at the University of Iceland. So Louise, she was born in 1988 and grew up near Copenhagen in Denmark. She has a bachelor and a master's degree in physics from the Niels Bohr Institute at the University of Copenhagen, where she studied from 2009 to 2014. In 2015, she started her PhD, her doctoral studies here at the university that she is now defending today. The opponents at this defense will be Dr. Sean Marshall, who is sitting here next to us, professor at the University of Calgary in Canada, and Dr. Xavier Vetwijs, he is a research associate at the University of Leeds in Belgium. So Dr. Sean Marshall, he is a glaciologist with experience in glacial dynamics, cryosphere climate processes, paleoclimatology, and mountain meteorology. And Sean is familiar with the Vatnajökull, I believe, from his modeling efforts with colleagues here at the University of Iceland. So he knows the subject, you know. So Dr. Xavier Vetwijs is an expert in using regional climate models to simulate the Greenland ice sheet, climate and surface and mass balance both in the past and present and future, I guess. So the PhD defense begins with the candidate presenting the results of her thesis work, followed by the examination of the opponents, who will discuss the thesis, ask questions, and you are supposed to answer those questions. According to the regulations of the University of Iceland, others who are not opponents can discuss the work of the candidate if they have requested to do so with a 24 hours notice. Well, nobody has made such a request, so we can just continue. Okay? So the candidate will now present her research, an overview of her research, and I suggest me and the two of you, we can just sit here in the front row. Okay? So Louise, the floor is yours.
Yes, thank you for the introduction, and thank you all for being here. I'm just going to start by giving a little bit of a general introduction to the subject, and then I'll go into some of the results of my PhD. And as you all know, ice caps and glaciers have been losing mass at increasing rates as a result of a changing climate. And glaciers are a very important component of the Earth system, and they're also a very vital source of natural resources. On global scale, they, for example, contribute to the rise in sea level, whereas on regional scales, they, for example, control the hydrology of rivers, which is used for hydropower production and irrigation systems. And it is therefore quite important to investigate how the glaciers respond to climate change, both on global as well as on regional scales. And Icelandic glaciers are not very big players in terms of sea level rise, as the entire volume of ice is only equivalent to a 1 centimeter sea level equivalent, but they're very important, for example, for hydropower production in Iceland, and they're also very sensitive to changes in climate, so they're a good proxy for climate change. In addition, many of the temperate outlets from Icelandic glaciers they resemble some of the Løn terminating outlets from southwest of Greenland, and they can therefore be seen as an analog for what will happen to the Arctic glaciers during a warmer and wetter future. But the focus of my study has mostly been on Vatnajökull, which is the largest glacier in Iceland as well as Europe. And the overall aim of the project has been to improve the predictive capabilities of surface energy balance models applied to estimate the melt of Icelandic glaciers. So I'm just going to give a bit of an overview of what determines glacier melt, as well as what kind of models it is that we aim to improve, before I will start talking about these improvements. And the amount of melt from a glacier is determined by the energy balance, which is the sum of all energy components at the surface. I have written out the ones that are most important for Icelandic glaciers here, which include the incoming and outgoing long-wave radiation. Then we have the incoming short-wave radiation, or the solar radiation. And the amount of short-wave radiation that is absorbed by the surface depends on the albedo, which is a measure of the reflectivity of the surface. And if we have something that's a very fresh snow, that's very clean and white, we have a high albedo, which means that most of the incoming radiation is reflected off the surface. Where if we have something with a darker surface, we'll have a lower albedo and less energy will be reflected, and therefore there will be more energy available for melt. The energy balance is therefore very sensitive to change in albedo, and it's very important to have accurate estimates of this. Then we also have the sensible heat flux, which is the transfer of the air's heat, as well as the latent heat flux, which occur to energy released or absorbed during a phase change. Now, if the energy balance is negative, then the glacier loses heat and the surface cools. But if it's positive, it can be used for one of two things. If the surface of the glacier is below the melting point, then the energy is used to heat the glacier. But if it is at melting point, then the energy is used to melt the surface. And the energy balance components can be observed by automatic radar stations that operate on the glacier surface. These have, for example, been operated on Vatnajökull since 1994, with between 1 and 11 stations on the ice cap over the summer months. And how they work is that they observe the radiative components at 2 meters above the surface. And the turbulent fluxes are not measured directly, but they can be estimated by observing the temperature, humidity, and wind speed at 1 or more level above the surface. But if we don't have any observations available, or you want to do future projections, of course, then there are no measurements available, and you have to simulate each of the components of the energy balance. And to do this, I have been using climate models. And on the larger scale, there are what are called global climate models, which model the entire planet. And these are numerical models which combine atmospheric and surface ground physics. And the problem with global climate models is that because of the large domain, they're normally run with 100 to 200 kilometer resolution, which means that the Icelandic glaciers would not be resolved at these scales. There's another kind of global data set that I should mention, which is a global model where you combine all available observations for a certain period with a numerical forecast model. And since this kind of reanalysis is based on observations, they generally do better simulations of the past than the global climate models, which are not based on observations. However, how well it does for a specific area depends on how many observations are available, and in areas such as the Arctic, where there are not as many observations, it depends on the scale of the forecast model used. But if you want to look at just a smaller area and look at it at a higher resolution, you can do what is called a regional downscaling. And this can be done via a regional climate model. So what you do is that you take an area and run it at a higher resolution by forcing it the lateral boundaries by a global climate model. And the resolution of these models varies very much depending on the size of the domain as well as the kind of model used, but you can get very high resolution models that has resolutions of 1 to 5 kilometers, and in these models then the Icelandic glaciers, at least the larger ones, can be resolved. So this is what I've mostly been focusing on. And none of these models include any kind of glacier dynamic, so that means they basically have a glacier mask that you put into the model, and that does not change no matter how much the climate changes. So if you want a glacier that can evolve dynamically as the climate evolves, then you need to couple an ice flow model. And there are two ways to do this. One is to just force the ice flow model with the output for one of the climate models. But the problem with this is that a lot of the components that you calculate with the regional climate models are depending on changes in surface elevation. So ignore some very significant feedbacks by doing this. So a better way is to have a two-way couplings between the two kinds of model, although this is also quite difficult because there's a lot of computational challenges with this. But this brings me back to the overall aim of the project, which was to improve the predictive capabilities of these models, more specifically regional climate models. And the results of my study has been summarized in 3 papers. The first has been published in the Cryosphere and deal with model validation and improvements. The second, which has been published in Atmosphere, deal with more model improvements as well as sensitivity studies. And the third paper, which is hopefully almost ready to submit, deals then with future projections, and we also start to bring in an ice flow model. And the 3 papers build pretty well on each other, so I'm just going to go through them chronologically. And the aim of the first paper is to validate the regional climate model that we're using, which is called HRM5, for simulations of the mass balance of that vehicle. And this is done by doing simulations of the recent past and comparing it to available observations. In addition, we try to make some improvements to the albedo scheme, because as you can see in this picture here of the summer surface of Greenland and that vehicle, Greenland has this very white, clean surface, which means that a lot of the incoming short wave will be reflected, which is not quite the case for that vehicle, where we have these very large, these very dark areas in the ablation zone. And this is because there are tephra layers in the ice. That means we have this very low albedo. So we also try to make some model improvements to take this very low albedo into account. And Vatnajökull is actually a pretty good area for model validation, as there's been a long-term observational program since the mid-90s. The observations are also concentrated over a relatively small area, as opposed to what they are for example, Greenland, which means a good area for testing the spatial variations within the model. And the first data set I've been using for validation is from automatic weather stations, which have been operated on the glacier since 1994. I have mostly been focusing on 5 stations, 2 on Tunnajökull and 3 on Broajökull, which are marked with the little triangles up there. And I've used those because they've been operated at approximately the same location since at least 2001. I also get a bit of the few different areas of the glaciers, as I have 2 in the accumulation zone, 2 in the ablation zone, and 1 near the ELA. In addition to this, I use observations from mass balance surveys, which have been conducted twice a year since 1992, with an average of 60 sites every year. And this gives me estimates of the summer, winter, and annual mass balance at a lot of locations. And in addition to observations for model validation, I also use observations for model improvements. And here I use satellite observations from the moderate resolution spectroradiometer, which does observations of the albedo. And I use these observations to create an ice albedo map in order to capture the very low albedo and the spatial changes in the ice of Vatnajökull, so I can incorporate this effect into the model. And to do this, I use data from 2001 to 2012. And the model that I'm using is called HRM5. It is a hydrostatic regional climate model that for this study was run with a 5.5 kilometer resolution over Iceland, and it was forced by reanalysis at the lateral boundaries. And very quickly, the albedo scheme that we're using has a snow albedo that decays exponentially as a function of the time since the last snowfall, as well as the temperature. Then we have a smooth transition between snow and ice, and then the ice is determined from this background map that we're creating from satellite data. And the way we do this is basically that we throw away any years with volcanic eruptions because we don't want the effect of this extra tephra. And then we just find the minimum value in the autumn of every grid point and say this is the value of the ice albedo. And then in the end, we have a full map of the ice in the ablation zone. And the way that we incorporate this into the model is a little bit important because this is a method that I use throughout all 3 papers. And basically what I do is that I run the snowpack scheme from HRM5 separately from the atmospheric component. So I have a simulation of HRM5 where the atmosphere and the snowpack will run simultaneously, but I do not have any of the improvements to the albedo scheme. From this, I take out all the atmospheric, the meteorological components that I need to force the snowpack scheme, which is the incoming radiation components, the turbulent fluxes, as well as the incoming mass fluxes. And then I use that to run the snowpack scheme. This version of the snowpack scheme, I then incorporate any new albedo changes into, and then I run it from 1980 to 2014, but without updating any of the atmospheric components. And the reason that I do this is that it's a lot faster to just run the snowpack without the atmosphere, and it's a cheaper way to test any new model implementations. And in general, new model implementations is added into the model in this manner, which means that it's often several steps ahead of the full model. For example, it has more subsurface layers than the full model did. And since the only thing we're changing is the albedo, we expect the error due to feedbacks from not recalculating the atmospheric components to be small. So I did simulations with this new albedo map from 1980 to 2014, and I did a lot of model simulation comparisons with observations, but I'm not going to show all of them. I'm just going to show a few of them that I find the most important, starting with the albedo. And this is the albedo at 2 areas in the accumulation area. So these are, of course, not affected by the new ice albedo map, but in general, they do fairly well at estimating the albedo. The red is the simulation, the black are the observations, except for one very obviously outlier, which is 2010 and 2011. And these are 2 years where the glacier was affected by volcanic eruptions, which is, of course, not taken into account in the model, so these kind of deviations is to be expected. If we look at the 2 stations in the ablation area, we somehow see a little bit of a different picture. Here we get something that's in the first figure, which is from Boerjökull. The ice is generally exposed a little bit too late in the year, which means that we have an overestimation in the albedo. And in the lower figure, which is from the ablation area of Tunnajökull, the ice is never exposed in the model, which means we have this very high overestimation of the albedo. And the reason for this is that there seems to be an overestimation of precipitation in the model. So if there's too much snow on the surface, it will take longer to melt through all the snow before we can reach the ice. And in the case of the lower figure, we just never actually reach the ice. So the effect of this new albedo scheme doesn't really help much if we never actually reach the underlying ice. And it also doesn't help that in general, the energy balance components are a little bit underestimated for all of them. This figure shows a comparison between model and observations for 5 of the automatic weather stations and the different energy components. And although they're all underestimated a little bit, the clearly largest source of bias is in the short wave radiation, which is the green line. And sometimes that can't be helped. For example, at the upper station at Tunnajökull, where we had the effect of volcanic eruptions. But down here at the lower station of Tunnajökull was because we had too much snow in the model, and that is a little bit more unfortunate. And this overestimation in the energy balance, underestimation of the energy balance components, of course, is going to affect the surface mass balance calculations. And this is a comparison to all the available observations from 1992 until 2014. And the middle figure shows the summer comparison. As you can see, it's generally overestimated for most of the points. But if you look at the winter balance, that is really where we have one of the biggest errors, which are all the white points. They're very far away from the one-to-one line. And these are all from one point, which is Boerjökull. And this is an area with very high orographic precipitation. And if you take an area with a lot of precipitation and overestimate with about 100%, of course, that's going to lead to big biases in the model. This can also be seen when we look at specific mass balance of the entire ice cap. And you can see in the winter balance, we have about 0.5 meter overestimation overall, which really is quite a lot. But if we just take the Boerjökull points and we say we know it's overestimated by about 100%, and we just correct for this, then we get something that fits much better. So one of the biggest problems that we have with the simulation of the winter balance is in these areas with high orographic forcing. The summer balance looks a lot better though. In years with volcanic eruptions, it's generally a little bit overestimated, but overall it fits very well. Which just shows that although the model didn't capture the spatial variation in the summer mass balance very well, it do seem to capture the overall trend. So after having done this evaluation, one of the biggest problems we had was obviously with the precipitation. And because it means that we have an overestimation of the albedo in the ablation zone, and we also have this overestimation in areas with high orographic forcing. So this made us start to consider what kind of model changes could improve the precipitation. And this leads me to the second paper, where we try to bring in a different model to provide meteorological forcing in order to try to improve the simulations of the mass balance. In addition, in this paper, we do a bit of a modeling experiment to estimate the effect of the spring snow thickness on the summer runoff. But the first thing we wanted to test is figure out how we can improve the precipitation. And one way to do that could be to move to a higher model resolution. And there are two reasons for this. One is that the topography will be better resolved, which will improve the orographic precipitation. And the second is that at resolutions better at about 4 kilometers, then non-hydrostatic processes, such as deep convection, can be explicitly resolved in the model. And in many regions, this is a dominant source of precipitation. In order for this to be modeled correctly, it does mean that you need a shift in the model dynamics from a hydrostatic to a non-hydrostatic core. But if you do this, then that will also improve the precipitation. Another reason could be the way that the model handles the precipitation. As in HERM5, it is considered to be a diagnostic variable, which means it's not a derivative of time. When the right conditions for precipitation are met, it's just placed on the surface immediately without any redistribution as it falls. And in some areas, the redistribution as the snow falls through the air can be quite important. So if we include something that has a prognostic theme, which means it's a derivative of time, that might also improve the precipitation. We therefore decided to bring in a model called Harmonia Rome because it fills all 3 of these requirements. It's a non-hydrostatic model with a 2.5 kilometer resolution over Iceland, and it also has this prognostic precipitation scheme. And a reanalysis project has been conducted by the Icelandic Met Office, where the model was forced by error interim reanalysis at the vertical boundaries in order to simulate the climate of Iceland back to 1980. So we decided to try to use the results of these runs to force the HERM5 snowpack scheme and see if this would improve the simulations of the mass balance. And the way that we do this is basically the same as we did before. Instead of having the online HERM5 run, we just have the Harmonia Rome simulations. We output exactly the same parameters, and we use that to force the snowpack scheme. And if we look at the results, this is a comparison between interpolated maps of the winter mass balance for periods of 1992 until 2014, and then compared to the simulations from the same period. And we use the winter mass balance as an estimate for the precipitation. It is generally assumed that the winter mass balance is equal to the winter precipitation. And as you can see, that while the pattern of the mass balance deviations are very similar in the 2 models, the value of the deviations is a lot smaller in Harmonia Rome than was in HERM5. This can also be seen when we model all the observations against the simulations on a 1-to-1 line. You can see that the Harmonia Rome simulations are generally much closer to a 1-to-1 line, and even the over-vehicle deviations, while they're still not perfect, they're definitely a lot better than they were before in HERM5. If we look at the other components that are needed to force the snowpack scheme, which includes the incoming radiation and the turbulent fluxes, they either do equally well as they did in HERM5 or a little bit better in terms of the short-wave radiation, which means that this seems to be a good improvement to the previous forcing. If you look at the specific mass balance again, you can see the winter balance is a lot better than it was before. We don't have this high overestimation, but the summer balance is about equally as good as it was before. However, for the model experiments we wanted to do for this paper, we wanted the simulations of the snow cover to be as accurate as possible. So we decided to introduce a simple scaling to the precipitation just to get some of the remaining biases to disappear. And this is basically just done by the difference between the winter mass balance observations and simulations, and then this is used to create a scaling map, which is then added to each snowfall event. And having taken steps to improve the precipitation, we can finally ask the main question of this paper, which is how sensitive is the runoff to changes in spring snow thickness, and how important is the snow thickness in the spring for short-term projections of the runoff. And to investigate this, we conducted a large set of model runs. And basically what we do is that we run the snowpack scheme from 1980 until 2015, and then save the state of the subsurface on March 31st of every year. Then this state is used as an initial condition for runs over the summer. So we take, for example, the spring of 1980, and then we run all the summers starting from this start condition, and then we do this for all the spring conditions. This means that we have basically a matrix of runoff values with 36 summers and 36 springs. So that means we have 1,296 model runs in the end. And this is the results of these runs. The gray area is the range in runoff for different spring conditions. And the red line is just the normal 1980 to 2015 simulation, where the summer fits with the spring. And the black line at the bottom is just a simulation I did where no ice is exposed to the model, just to have a lower amount of how much runoff there can be. We decided to focus on both the entire ice cap, but also look at some specific outlets to see if there's a difference between the different outlets. And here I've shown Borjökull, Síðujökull, and Skaftá glacial water catchment. And as can be seen from this figure, the gray area is definitely the largest in Borjökull, and that means it's the most sensitive to changes in the spring snow thickness. If we look at the minimum and maximum runoff due to changes in the spring snow thickness, Borjökull has a 53% increase, whereas Vatnajökull overall only has a 20% increase. We also decided to look at how much the variation in spring snow thickness or the summer weather affected the variation in runoff. To do this, we calculated the standard deviation in the runoff when we altered the spring conditions but kept the summer constant. And we also did the opposite, where we calculated the standard deviation in runoff when the summer was altered but the spring condition held constant. And as you can see, the standard deviation is a lot larger for the altering summer than it is for the spring, which means that the summer definitely has the largest effects on the changes in runoff. But again, it's Borjökull that has the largest effect of the spring conditions, and it's about 50% of the standard deviation during the summer. And the next figure basically shows exactly the same, but this time we have spatial maps. So the first one is varying spring conditions, then varying summers, and then the difference between the two maps. And the scales of the maps are similar. So as you can see, the summer balance is definitely the most controlling of the changes in runoff, which is not a big surprise. But although the spring conditions still are very important, they're definitely not the driving factor between the amount of runoff. The one exception is at the outer limit of Borjökull, which is up here, where the spring and summer has about equal effect. And this leads me then to the final paper, where we finally start to do some future projections of Vatnajökull under different climate scenarios. And to do this, we bring in an ice flow model called PISM, which has been applied in various studies of Greenland and Antarctica, but it has not yet been used for Vatnajökull. And what this does is that it solves the shallow ice approximation with a non-sliding base in parallel with the shallow shelf approximation, which is then used as a sliding law. And we use a few different climate inputs to force this ice flow model, starting with, for simulations of the recent past, we used the simulations that we did in paper 2, where we used harmony of Rome to force the HIAM 5 snowpack scheme. And this we have from 1980 until 2016. Then we start with future simulations. We first have the HIAM 5 forced by the global climate model Easy Earth at the lateral boundaries. These are run at a 5.5 kilometer resolution, and we have it for two different climate scenarios, RCP 4.5 and RCP 8.5. And these are scenarios for how much greenhouse concentration there is in the atmosphere by the end of the 21st century. And RCP 4.5 is equivalent to about a 3-degree increase over Iceland by 2100, and RCP 8.5 is about 4.7 degree increase. Because of the relatively high resolution of these runs, we only have them at time slices and not a continuous run. So we have one historical time slice and two future time slices for each of the RCP scenarios. In order to have more model projections to look at to see how the simulation changes when we look at different models, we bring in models from what is called the Codex Initiative, which is an initiative to advance and evaluate model use for regional climate, regional downscaling through international cooperation. And through this, a collection of future simulations from many different regional climate models have been made publicly available. And the highest resolution you can get for this initiative is a 12-kilometer resolution over Iceland. And we ended up using 11 models under the RCP 4.5 scenario and 15 under RCP 8.5. And the way that we used the regional climate models as forcing for PISM is basically, first we do the same as we did in the other two papers. We take the methodological output from the regional climate models, use that to force the snowpack scheme, and then we get simulations of the surface mass balance. This is then used to force the PISM flow model. There are a few more inputs we need to put to PISM in order for it to run, including an estimate of the bedrock topography, an initial ice thickness, as well as the geothermal heat map, and all of these are then based on observations. And after we input this, we, for example, get estimates of the surface elevation and changes in the glacier geometry. And as I mentioned at the beginning, when you use this way to force the ice flow model, then you ignore important feedbacks between the energy balance components and changes in the surface elevation. And unfortunately for this paper, it was not possible to do a two-way coupling between the two kinds of models, but I decided to try to do a little bit of a correction to see how much of a feedback it is that we neglect. And I do this by first doing a precipitation correction via precipitation lapse rate to the rainfall and snowfall. Then I do a temperature correction to some of the components that can be estimated from the 2-meter temperature, which is the incoming long wave and the sensible heat flux. And also do a correction to the rainfall and snowfall. So if the temperature at 2 meters above the surface is above 2 degrees, then the snow is turned to rain. This takes a lot longer to run than just using the one-order forcing, so I'd only do this for a few of the simulations. But before I can do any kind of future simulations, of course, I first have to initialize the model. And I do this using a constant climate spin-up. And this is basically just to make sure that the model is in balance with the forcing that you're using, so that any changes in the geometry are not due to changes in just the model of reacting to changes in biases in your forcing, but it's actually reacting to changes in the climate. And to do this, I use harmony arome forcing from 1980 to 1999, because the glacier is approximately in mass balance during this period. And I run it for 1,000 years until we reach a steady state. And the steady state, we get a volume that's about 3% too large and an area that's about 3% too small. But this is pretty much to be expected, because most of the major outlets of that miracle are surge type, which is not something that's taken into account in the model. So surges are these high velocity periods where excess mass is brought from the accumulation zone down to the ablation area, so therefore thins the glacier and also makes them longer. And if we don't include this effect, then of course we're going to have something that's a little bit too small but a little bit too thick. So consider we don't include this effect. It's an okay initial state. And the first model forcing that we use is from here on 5, forced by easy Earth at the lateral boundaries. And this is just a comparison. Well, this just shows the mass balance in the model for all 3 time slices. And for the first time slice, I've compared the observations with the simulations. And as you can see, it doesn't fit nearly as well as it did in the first paper when we used the analysis, and we have this large overestimation of the mass balance. And this is because the global climate model that we're using, Easy Earth, has a 2-degree bias, cold bias over the Arctic, which of course means we're going to have an overestimation of the mass balance. So in order to not include these large anomalies into the simulations, what I do instead is that I run the model with mass balance anomalies instead of the absolute values. So I just compare each of the time slices to the historical period, and then I run it with the differences. And yeah, this is the first simulations. What I do first is that I use 1980 to 2016. I use the analysis simulations. And from 2017 until 2100, I use the Easy Earth climate anomalies. And then in order to get a little bit of a longer time series, I say, what if the climate stabilizes after 2100 and continues to be the same for the next 200 years? Then what happens? So I repeat the forcing at the end of the century for another 200 years. And these are the results. And the continuous lines shows the results when I don't add any kind of elevation corrections. And the bottom figures just shows the change in area at 100-year intervals. And by the end of the run, in the RCP 4.5 scenario, I have 55% of the volume left and 75% of the area. So clearly the volume responds a lot quicker to changes in climate than the area does. The same is the case for the RCP 8.5 scenario, where I have only 15% of the volume left for 35% of the area. Now the stipple lines are when I try to add this elevation correction. And then I get something that has about 10% less volume and 10% less area in the RCP 4.5 scenario. So it is quite a significant effect of the feedbacks. And it's even more in the RCP 8.5 scenario, because here we have 14% less volume and 20% less of the area. And now this is only the results from one model. And so in order to test what other models would have as the future of that miracle, I bring in the Cortex simulations, as I mentioned earlier. And I have 11 simulations from RCP 4.5 and 15 from RCP 8.5. And it's important to mention that although these are with the same greenhouse gas concentrations, they are very different changes in the climate depending on which model you use. For example, if you look at the temperature, the model that has the largest increase in temperature and the one that has the least increase in temperature, there's about a 2-degree difference between the two models, which is quite a large span. The same is the case for the difference in precipitation. Some models have no change in precipitation at all by the end of 2100, whereas some has a 15 to 17% increase. And of course, this is going to affect the changes in surface mass balance by the end of the century. And by 2100, there's also about a 2-meter difference between the models, depending on which model it is you use in both scenarios. So we do exactly like we did before, and we again run with only mass balance anomalies instead of the absolute values in order to not include any kind of biases in the forcing. We get a quite large span in the areas by the end of the century. In the RCP 4.5 scenario, we have between 65 and 85% of the area left, and 35 and 70% of the volume. Whereas in the RCP 8.5 scenario, it's even worse, and we have 20 to 75% of the area left, and 5 to 50% of the volume. It is therefore very important to investigate what it's said in several models as well, because even under the same greenhouse gas concentration scenario, we can have very different changes in the glacier geometry. So before I end, I'm just going to give a little bit of an outlook as to how I see climate models of Vatnajökull are going in the future, if we had more time to work on it. And first of all, the move to very high resolution models definitely presents an improvement, even moving from 5 kilometers to 2.5 kilometers, as it's, for one, it gives improvements to precipitation, but as the resolution gets higher, we also get better at capturing the spatial variability, for example, in the albedo. In addition, it will be very interesting to actually do a two-way coupling between the ice flow model and regional climate models, although it does represent some quite significant computationally challenges because of the different scales of the different processes simulated by the RCMs and the ice flow models. But clearly, the elevation feedback has a large effect on the overall geometry, so it's important to test. And it's also important to consider the output from several models. As I showed with the cortex simulations, it's even for the same scenarios, they can have very variable results. Yeah, thank you for listening.
So thank you, Louise. Thank you very much. So this starts the question of the opponents. So Sean, you were going to start? So you go ahead. I'm just going to sit in front so I can see what you're doing.
Can you hear me okay? Yes? I'll begin by saying thank you, Louise, and your committee members and the organizers. It's a real honor and a pleasure to be here. I may be my 10th or 11th time to Iceland, and every time I'm overwhelmed with the hospitality, it's just a pleasure to be here. And it's maybe 15 years since I worked really hard and thought really hard about Vatnajökull, so this was really a nice chance to re-immerse and think about it. It's a fascinating and wonderful glacier that's very complicated and very hard to model.
Yes.
As you know better than anyone in the room, I guess.
Yes.
And I'm really impressed with the number of models that you've been working with and brought to bear in this study. It's a large, ambitious PhD research topic that you've taken, and I feel like you've really advanced our understanding in the field of modeling Vatnajökull. So congratulations.
Thank you.
I've many questions, more than I can work through in half an hour here. We'll take turns a little bit, but I'll start with a couple of my questions. And these are more, I think, for me to understand a little bit better. Actually, a lot of my questions are in your first two chapters that you've already published, so they've already been peer-reviewed, and people that understand this probably much better than I do have already approved this. So this is really just for my own clarification and understanding a bit, and maybe thinking forward to future work and the future modeling efforts and how you might think about things differently. Yep. And I'll start with albedo.
Yes.
Since the time I was working on modeling Vatnajökull, I've spent a lot of time thinking of mass balance modeling and climate downscaling and albedo. So everything in your thesis was really interesting to me. But can I ask you, just to start, what are the different controls of albedo, sort of spatially over the ice cap and also with time, temporally?
Well, there's a lot of different, yes. Well, one of the largest effects on the albedo is whether the ice is exposed or not, because there are these tephra layers in the ice. So once that's exposed, that's, of course, has a very big control on the albedo. Other thing that controls the albedo is, for example, melt layer pooling on the glacier, because if there's water on the albedo, that also lowers water on the glacier, that also lowers the albedo. There's the age of the snow, because of snow metamorphism and the change of the grain size. And yes, well, there's the temperature, because of there's the albedo of is going to be different whether we have a melting snow cap or not. Yes.
So those are the first order things.
Yeah.
That's good, and that's
Yes.
and most
and
of
the
those
solar zenith angle. For
and most of those are in your model,
Yes.
I guess.
Yes.
So the solar zenith angle. Can you tell me how that works?
Well, yes. You have the highest radiation when the sun is right above the surface, and then become smaller once we have a different angle of the solar.
And does it affect the albedo that you
Yes,
measured?
it does.
How does it change the albedo
It becomes lower
at the lowest zenith
at
angle?
lowest angle.
Yeah. So as I understand it, and I know some of these choices are inherited, it wasn't necessarily your study design, but so am I right from your thesis that when you're looking at the observed ice albedo, is it just the noon,
Yes.
that lowest zenith angle snapshot of albedo?
Yes, I used the one at the highest radiation.
Right.
At about noon.
So I'm curious, is that a source of bias, do you think? 'Cause this will give you systematically
we did check this in the beginning when I was doing the study to make sure if there was a big difference between them. But when you compare the ones that are calculated for the whole day and the ones compared for just the highest radiation, there's really only about a 1% difference overall, which we thought was a very tiny difference. So I really did not see that make any difference which one we used. And the noon one fit well with the modus proctor because that is when that one is taken. So that's kind of why I decided to use that one. Yeah.
So how did you calculate when you did that comparison of the noon versus the full day?
The noon versus full day, I plotted them up as a time series of all the available stations for all the available periods, and I did a root mean square error and did a percentage area over the entire simulations, and I also calculated what the mean bias was on a yearly basis, but also over the entire time series.
Okay. Now that's reassuring. If it's really only a 1% difference, I'm kind of surprised, but it's.
I mean, for some periods a little bit higher. The highest I saw was, I think, 6% for certain days, but overall it was very low.
Okay, no, that could be reassuring.
Yeah.
And then switching to MODIS a little bit, and comparing the observations to MODIS, do you know if you're comparing the same wavelength range for them?
Not exactly. The automatic weather stations goes to about 3 micrometers, and MODIS goes to about 5. So
Is that important, do you think? Is there much of an effect on
I don't think so, because there's so little solar radiation in the near-infrared spectrum that I can't imagine it has a very big effect.
Yeah. Do you know in the MODIS average, so as I understand it, again, the MODIS, you're using the 7 lowest bands, it goes from 0.3 to 5?
5, yes, exactly.
Do you know how that's averaged or calculated? Like, is it actually averaging albedo in those 7 bands, or?
Oh, I do not remember, no.
Do you know how snow and ice albedo change with wavelength? Have you seen those diagrams or plots? Can you describe for us?
Yes, I'm trying to remember.
Actually brought an image, but I won't bother to.
Yes,
I'll just let you describe it for us if you want. But is there a wavelength dependence to snow and ice albedo?
Well, yes, there is to both of them, right? I would say so, but maybe I'm wrong.
It's something to think about a little bit. The spectral reflectance is much higher at the lower wavelengths, so the visible band, and then it drops down to much more like an infrared, almost black body above 1 or 1.5 micrometer. It kind of stays there. So above 1 or 1.5 micrometer, it's essentially albedo of 0 to 0.05. So if you're just averaging directly from those 7 lowest MODIS bands, I really worry again that would be a really low bias to the albedo.
Yeah, okay. Well, I'm not the one who made the MODIS simulations. That was provided by someone in France called Simon Gascoigne, who's worked a lot with it. So he should know what he was doing, but I'm afraid I don't know the exact science behind it.
And specific to snow and to glacier applications? So.
Yeah, he has done it. He also done it specifically for Iceland. He's written a few papers about it.
Because I was definitely left worried a bit that you have systematic low biases in both the measured and the observed, and that's why they agree pretty well.
Well,
but overall It's perhaps too low, but...
Yeah, but in the observed, I have it just at a point value.
Yeah.
So I'm guessing it can be a lot lower than we have an average over 5 kilometers.
Yeah.
Because if it's standing on these Teffer layers, for example, then we're going to have a lot lower albedo than if we just average over the entire 5 kilometers.
Okay.
So that is kind of how I saw it, at least.
Okay.
At least one of the station accumulation areas sometime in the ablation area. Sometimes it was just standing on basically a layer of dust, which means we have low albedo. So.
No, well, and it's really true, I think, probably of the world's sturdiest glaciers.
Yes.
So you definitely have the lowest albedo, published albedo values I've ever seen, like less than 0.1 routinely.
Yeah.
And so I believe a lot of that's real, but I did worry a bit that it's systematically low.
Yeah, fine.
And that kind of leads into my next question, which is about the biases in the energy balance fields and meteorological modeling. So as I was reading through your plots that you've shown us and the overall Vatnajökull mass balance modeling, specifically the summer mass balance, seems pretty good. But when you compared it where you've got station data, and again, it's a place that's amazing about Vatnajökull. You've got the best, longest running weather station data that I've seen anywhere since the 90s. So you've got a really nice observational data set.
Yeah, it's really good.
When you compare that to most of the models you worked with, there's always these systematic negative biases.
Yes.
Right? In everything, right? Humidity, temperature, long wave, short wave.
Pretty much, yes. I think the outgoing long wave is pretty much the only one that fits very well. But yeah. Yeah.
So I guess I'm surprised that the model doesn't underestimate the melt.
Yes, that is a good point. If you just go back to the... Well, yes. Well, here I kind of assume it's because most of the points are on the kind of the northern end of the glacier, and we don't have a lot in the southern.
Yeah.
We don't have any measurements. But if I can compare it to kind of interpolated mass balance maps, which are not based on observation, but it's based on kind of educated guesses, I do have fairly large overestimation of the melt in, for example, Skeiðarárjökull, and also a little bit in Breiðamerjökull. So I assume it's because the different area of the glaciers equals out, and that's why maybe, but since we don't have any observations there, it's kind of hard to say. But when comparing to those maps, I definitely get an overestimation of the melts in Skeiðarárjökull, for example, and a few other areas on the southern coast.
So do you think then when you're expanding to the whole ice cap, it tends to just balance out positive and negative?
Yes, which is kind of lucky, pretty much, but yeah, I think that's the case.
Yeah, it's interesting. So you didn't bias correct your
didn't,
meteorological forcing at all?
No, I didn't. The only thing I corrected was the vehicle points for the winter balance, and that's it. Okay. The rest I didn't do anything to.
I mean, it's a good result, but it just surprised me a bit because the incoming shortwave bias.
Yeah, I was a bit surprised as well because when you look at the automatic weather stations, it's all overestimated by a fairly large amount.
Yeah.
But, Do
you think there's any? I guess my concern, linking those two comments so far, was that you're getting away with it because the albedo is too low.
Yes.
I think that's possible that you're getting okay results because of cancellation of errors, negative incoming fluxes of sensible heat and net radiation, but then too low in albedo, so you end up with an okay answer, but for two
that
errors.
Could be, yes. Yeah, that could be. A little bit, yes. But
I'm not saying that's what happened because you will know the best. You've stared at these so much, but it's something to think about a little bit.
No, I thought about that too, that maybe it's just that I'm kind of lucky that they're kind of evening out because I do have significant biases that it's just kind of lucky that it's evens out at the end.
Okay, those are good answers. Thank you. I'll maybe one more question, and then I'll pass over to Xavier. I'm curious about the snowpack model. It's a very sophisticated snowpack model in here, M5, which seems state of the art. This is really a growing field of doing the snowpack really well. Yeah. How important do you think it is for Vatnajökull to really model and detail the surface snowpack layers?
Well, I mean, one of the reasons that it's important for Greenland is because of melt refreezing, which is not a very big effect on Vatnajökull. So in that sense, it's not that important, but I think it's still important because we model the depth of the snowpack fairly accurately, which is of course important for when the ice is exposed in the model, and we also get a good estimate of the amount of water in each layer as well as the density profile throughout the ice, which I think is important. But no, I wouldn't say it's as important as, for example, places where they have a lot of refreezing. Yeah. But
is there some meltwater refreezing?
A little bit in the spring, yes, but not very much.
Okay. Yeah. Have you calculated it to see if it's very important for the energy or mass balance?
I did, and it wasn't. Yeah, it was very little.
Yeah. How does that model treat rainfall coming into the snowpack?
Well, it just assumes that rain is at 0 degrees, so there's no additional heat because of rain, and then it percolates to the model, and either it refreezes if it can, but otherwise it basically just percolates to the layer until it reaches an impermeable layer, and then it runs off.
Yeah.
And since we don't have a lot of refreezing, then most of it just runs off.
Yeah.
Yeah.
I was interested in, this jumps ahead to the last chapter, but some of your work with the PISM model, with the polythermal version, it was giving cold-based parts of Nyoko, which was a surprise.
It was a little bit weird, yes.
So do you think do you have an idea where that's coming from?
Well, there's only very small areas where it is actually cold-based. It's at the edge of Boreal, like right here, and the edge of Dynøyakul. The rest remains. So it's a very small area where it actually is.
Okay. And
my best guess would be then the model, the cold layer, the cold wave actually penetrates through the snow in the model, which is not, we know from observations that it does not. Yeah. But my best guess is that it does this in the model, and therefore we have this underestimation. But no, most of it is tempered. It's just those two little problems.
Okay. Yeah, my question about that was related to that cold wave.
Yes.
The meltwater refreezing, but you are capturing any latent heat release from meltwater refreezing.
Yeah.
There, so that's in the model, so it should.
Yeah.
Even with that, it's still wanted to be cold there.
Yeah, exactly.
Interesting.
So.
Okay, I'll come back to some of the glacier modeling after we loop around, but I'll pass off here. Thank you.
Okay.
First, Louise, I would like to congratulate you for your job, because probably your original aim of your PhD was to couple ERM5 and an ice shield model, but due to a lot of problems of modeling, you needed to change the model, you need to apply correction, your forcing was too cold, and I have exactly the same problem with my model MAR over the Greenland ice shield. Yeah. And I have like a lot how you deal with all of this problem of modeling, because I think with the current state of climate model, it's quite impossible to directly couple an RCM with an ice shield model, because there are too much biases in each model, and in the forcing also. But I have some questions for you about mainly the RCM part of your PhD. My first question is about the initialization of the snowpack.
Yes.
Because probably for the spin-up year, you have used the raw ERM5 output, or have you used corrected ERM5 output?
Just ERM5 output. I didn't.
Yes.
Corrections.
Because in this case, probably you could underestimate the bar ice area. Because the model overestimates precipitation.
Yes, I do a little. That's true. I do a little bit. Yeah, I have a little bit too big accumulation zone.
Yes, in respect, and perhaps this could explain some biases.
Yes, it could. I think, for example, at the lower Dynøyakul station, where I get this large bias in the Albedo, could be because my accumulation area is a little bit too big, which is why I never actually reach the underlying ice, because it thinks there's a layer of.
Yes. Yeah. Perhaps if you need to make another simulation, perhaps it should be good to initialize your snowpack with corrected precipitation. Yeah, true. Because it's the same also for the Greenland ice sheet, but the snowpack results are very sensitive to the bar ice area.
Yeah, true. I mean, for the second paper, when I do start adding corrections, I do have a little bit of a correction in the initialization as well.
Yes, okay.
But not in the first
paper. Not in the first paper. Okay. Now it's about your biases of precipitation. Could you show the slide with perhaps the biases with the two models?
Yes.
I think perhaps?
This one.
This one. Yes, this one. Because when perhaps I made a mistake, but for me, most of the precipitation come from the southeast in this area.
Yes, it does.
And therefore, we have a big topography, and we have, in both models, the barrier effect, the blocking effect is too high.
Yes.
In respect to what we observed.
Yes.
And therefore, my first question, you have well explained in your presentation the differences between diagnostic and prognostic precipitation, and the interest of using prognostic precipitation. Have you tried to decrease or increase the precipitation velocity in your model?
I have not, because I was not the one running with harmony of Rome simulations. It's just something I received from the Icelandic Math Office, so I've not actually run it myself.
Okay.
But I think you're right that could probably...
because with MAR we can play with this parameter,
yes.
and this can change a lot of the precipitation pattern.
Yes.
And I think perhaps one of the problems could be this.
That is something we talked about, that when the models were at a lower resolution, then this parameter was just tuned, so it would fit with geographic precipitation, but then when they became at a higher resolution, then maybe this parameter is a little bit too high.
Yes, perhaps you need to decrease.
Exactly.
And my second question about this biases, it's about your simulation. You have directly forced your model by the error-tearing field without intermediate simulation.
Yeah.
Because here the resolution of error-tearing is 75 kilometers.
Yeah.
And here you run your model at 5 or even at 2 kilometers.
Yes.
And I think there is a big gap.
That is a very big downscaling, that's true.
Yes, yes. And think if you use the new AR5 analysis, which are available at higher resolution, this could improve your result.
Yeah.
With MAR, I have seen that if the gap between resolution is higher than 10,
yes,
you can have problems. And
yes,
it is,
I write that in the
yes,
piece
it
as
is
well,
your
yes.
case.
Yes,
yes,
I know. Yes, that's true. But as far as I know, this was not run with a model in between them. It just has a relaxation shown of about 10 grid points.
Yes, yes.
But it is, it is kind of at the limit to where how far you can downscale down without having.
And probably, it is mainly the case for the GCM because the gap is even higher.
Yes.
Between when you use GCM.
Yeah.
And my last question about this is, look here, you have too much precipitation upstream and too low downstream, downwind. But have you any idea about the transport of the snow by the wind? Because if you have a lot of wind, you can have a transport of the snow from the margin of the ice sheet and behind the ice sheet. Do you have some measurement about this?
Yes, there are no observations about this.
Yes.
But the general feeling is that, in general, it's not very important for the ice cap, but it can be important in years where we have very strong winds in the same direction for most of the year.
Yes.
And also if we have dry snow, which for Vatnajökull is fairly uncommon, but it can happen that we then have a large mass transport. But in general, it's not expected to be a big effect.
Yes.
Okay.
Yeah. Okay, I have now a question about your correcting matrix.
Yes.
The next slide.
Yes, this one.
Yes, this one. Because when we see this matrix at the side, there is a factor 10.
Yeah, it's a very big.
It's a lot.
Increase,
it's a lot.
Yeah.
Are you sure that the measurement that you have used for building this matrix are reliable or are representative of the area of the south?
Well,
yes,
that's a good question, yes. And I can't really know for sure because we only have those observations. And
because you have only observation on one point.
Yes, exactly. And that is, in the beginning we had talked about making a scaling relation where I create from the points, I create some kind of linear trend or something that I can do with precipitation.
Yes.
But because I have so few points there, I didn't really feel like I could make a scaling for so few points, which is why I decided to use the map. Because although it's based on guesses, at least it's based on somewhat educated guesses, and it's the best estimate we have of the mass balance, but I mean, we can't know for sure that it's not. There are no biases because there's no observations.
Yes.
So yeah. So it's the best we could do, but
yes. But you need additional measurement. Yeah. Perhaps we need to perform some measurement fields in this area.
Yeah, it's a hard area to conduct measurements, though.
Yes. About this correction is only applied for the winter precipitation?
It's also applied for the summer precipitation.
Summer precipitation,
yes.
And only for snowfall or also for rainfall?
For rain and snow.
Rain also, yes. Okay. Because it is not clear in your manuscript.
Yes.
But okay. Perhaps it's okay, but...
Yes.
And my last question about this is about the circulation changes,
yes.
general circulation. Because if we assume that we need, to apply the same correction every year, you assume that the general circulation is the same every year. But in reality, it is the case, for example, in summer, what we have observed some change in the North Atlantic Oscillation.
Yes.
We can have significant change of the origin of precipitation, of the precipitation pattern, and so on.
Yeah.
Do we have an idea about these uncertainties? Or perhaps the internal variability of...
I made
you
made an extra slide.
Yes. Okay.
Yes. Precipitation patterns.
Yes.
Exactly.
Okay.
Well, this is just how many of them, and I compared the winter precipitation pattern with the summer precipitation pattern overall. I think they are very similar in general. The biggest difference is that just less precipitation in
summer. Yeah.
In summer, yeah.
Okay.
There are some months where we see something where the precipitation comes in, and there's a lot of precipitation over that vehicle, which does happen occasionally, but overall the precipitation patterns are pretty similar.
Yes,
Yeah.
okay.
But, I mean, sometimes it does look like this, and then the correction doesn't really fit as well. But, yeah.
Okay. Now I have a question on your last paper about the coupling. And my first question is about the correction of precipitation. Perhaps you can show the slide where you explain the different steps.
Yes. Yeah. Yes.
Yes, this one. But first, you use a present state which is forced by harmony, arome.
Yes.
And after that, you apply to this present state anomaly from IRAM5. Maybe.
Yes, exactly.
In the IRAM5 simulation, do you have used also the precipitation correction or not? For future projection also?
Yes.
Yes.
Yeah.
Because it is not clear also in your...
Oh, sorry.
Okay.
Yeah, I included in the future presentation as well.
And about this simulation, look, you have shown in your manuscript that IRAM5, in here also you have shown this. Perhaps you can show the time series.
This one. Yes.
Yeah, this one, yes. Look, due to cold biases in your GCM-based forcing, IRAM5 is too cold and so on. Are you sure that if your current climate is too cold, if you have a significant too cold climate over current climate, and now if we compute future projection, I think a part of the signal in anomaly could be impacted by the biases over current climate.
Yes.
And it is, for example, the case between precipitation, or about precipitation, the distinction between snowfall and rainfall. Because in future we should have a big increase of rainfall and correction of snowfall to rainfall.
Yes.
But here you're probably over current climate, your model simulates in the summer probably too much snowfall, and therefore the anomaly of snowfall rainfall should be impacted by biases. Do you have some idea about this problem?
Well, I mean, that could very well be, because this is one of the models that estimate the largest changes in the mass balance, so that could be because of this effect of rain versus snow.
Yes.
But since it generally simulated the other parameters very well, and it just had this bias in the temperature, I thought maybe it would still be able to simulate the variations in the climate. But, I mean, I can't know for sure. I don't have estimates of the future mass balance. But no, I hadn't thought of that, but it's a good point.
But in your snow model, when you force your snow model, if you have snowfall with positive temperature, you convert snowfall to rainfall or not? Or you just use the...
I mean, when I do the correction here, then I convert it to snowfall to rainfall. But for the other ones, I don't. Then I just use the mass balance anomalies.
Yes,
I
okay.
don't convert anything.
Yes. Look, you have used about your lapse rate for the correction here. The lapse rates are constant in time and space. Yes. And have you tested the impact of the value that you have used for this lapse rate?
I tried to do like a 10% increase and decrease in the simulation and see how that would affect my mass balance. And it was about a 2% change per year. So it wasn't a huge change when I did a 10% decrease or increase. And it was about the same for precipitation and temperature. It was about 2% plus minus.
Yes.
So it's not hugely sensitive to
yes,
it.
it's quite robust.
Yeah.
Okay. And I have also just a remark. So in your, you have not shown here, but in your manuscript, you remove completely your ice cap, and after that you try to rebuild the ice cap. And I think if we come back to the current climate, if you without your ice cap, I think a large part of precipitation are due to topography effects.
Yes, definitely.
And if you remove the ice cap, I'm not sure that you can use the present precipitation rate with some correction and to apply it.
I am aware it's a very rough way to do it. That it ignored a lot of different things, and the only feedback we have on the changes, we affected a little bit because we have an elevation lowering, because then we affect it that way, but no, we don't really take into account the effect of precipitation patterns as coupling. So I think you're right, it's not going to be exactly the same.
Yes.
Yeah, we kind of knew that.
But I think it's for this reason that a coupling between an RCM and an ice-sheet model is needed.
Yes, I think
because, for example, for general ice-sheet, I have exactly the same problem. For the melt, it's okay. We can use a lapse rate, it's okay. But for the precipitation, it's completely different.
Yeah, that's
and
true.
When and also a larger part of snowfall become rainfall, and this impact a lot.
We basically just included the effect of the change in elevation. We didn't include the effect of changes in precipitation patterns. So it didn't become that complex now.
And my last question is about your Cordex simulation.
Yes. This one.
Okay, I have liked that you have used a lot of forcing just to test the sensitivity of the forcing. But are you sure that in the Cordex simulation, the resolution is 15 kilometers or 12 kilometers? And I think at this resolution, we are not able to resolve your ice cap.
Not very well. I added an extra slide of that to Cordex. No, that is not. Yeah, this is the shape of the ice cap. So it's, when I outline the shape of it on top of it, you can kind of see it, but without it, it doesn't really look like the right shape. So it kind of captures it, but not quite.
Not quite, because I think in the anomaly you compute a large uncertainty. For me, it's come from the resolution, because the model are not able to resolve explicitly probably the altitude of your ice cap. And therefore the anomaly are biased by this.
It's of course affected by we're not able to resolve the ablation area where you have this very low albedo and stuff like that. But when I compare to the 5.5 kilometer simulations, it does give very similar results still in the changes in geometry. I think it was only a few % difference if I used here on 5 forced by easier the 12 kilometer resolution or the 5.5 kilometer resolution. So for this reason, I assumed that it at least kind of captured it, but it's, as you can see, the shape is not as...
Yes, because you have shown a slide that your simulation using IRAM5 simulate a higher change in respect to all the Cordex simulation.
Yes, it does.
And probably, I think it's probably due to the differences in resolution, because IRAM5 is able to simulate polar climate.
Yes, I think so too.
And therefore, with a warmer climate, we can have big differences in climate. And in the Cordex simulation, we are already at the state of not a polar climate, and therefore the changes are smaller.
No, I agree. I also think that's why I have the largest mass balance anomalies in the 5.5 kilometer resolutions compared to any of the others. But it was just to get an idea of what different models would.
Yes. It's no problem with it. Thank you.
I'll pick up a bit again, if I can, on the climate downscaling, if you want to go back to your flowchart for this.
My flowchart, yes. That was this one.
Yeah. I just was curious about the elevation correction, both in the surface energy balance modeling, but also in the mass balance modeling. And as I read this, the way you do it is you're calculating the energy fluxes within the RCM, within the regional climate model, and then you're correcting as a function of elevation, the sensible and heat flux and the long wave radiation.
Exactly.
Is that right?
Yeah.
So you're essentially modifying those, or are you going back to modify the temperature and then recalculating?
I modify the temperature and then I recalculate it.
Okay.
I say that these two can be estimated as a function of the 2 meter temperature.
Yeah.
And then I change the temperature and then I add a correction based on this.
So those ones I'm probably comfortable with.
Yeah.
But the other energy fluxes, I guess it's mostly just latent heat flux. You just leave directly from...
Yeah, I leave that. I know that the humidity changed a bit as a function of temperature, but I wasn't quite sure how to add this into the model simulation, so I didn't do that.
Okay.
But
yeah, that's something that in your going forward, I think maybe in your third paper or as you proceed, it's the least important of those three energy fluxes.
Yes, I would say so.
So it's
exactly. I assumed
crucial.
it would have a very small effect, but I didn't really do any tests on it.
And it's probably true, but it's also possible to do that correction to recalculate that latent heat flux as a function of, with an elevation correction.
Yeah.
And it's nonlinear, so it's potentially more important than you think. It can flip signs and things like this.
Yeah, that's true.
Yeah.
And it is expected to have a bigger effect in a future climate, so it could definitely.
Yeah. And did you ever consider elevation corrections to the other meteorological fields like wind and humidity?
I did not. I know that they're important, but I did not consider adding any kind of any kind of correction to them.
How might you do something like the wind correction? Your winds were generally too low, is that right?
Yeah, a little bit.
Yeah. Is there any sense of how you might bias adjust that or correct it for elevation?
Not really, no. That's why I didn't do it.
Okay, yeah. The one thought I had is that I've seen a little bit done in the literature is if you would think about doing, looking within your RCM itself, the lapse rates already in the RCM for temperature, for humidity, for moisture variables, but also for wind in the lowest nearest surface layers, say the 5 nearest surface layers, that might give you a really nice even time varying lapse rates that could be useful to do a higher order version of this.
That's a good idea.
It's probably second order, you've probably got the main things, but you might also find interesting variations, that, as Xavier mentioned, in the temperature lapse rates from that.
Yeah, that's true. Good point.
And ask about just a bit about the mass balance field. So from this, you estimate the mass balance, summer and winter mass balance.
Yes.
And then when you're going into future simulations, are you recalculating the mass balance each time from these adjusted meteorological fields, or are you bias adjusting the mass balance itself?
For this one, I'm calculating it every time for the mass balance fields. Okay. So I'm using the meteorological parameter for every year and just recalculate. Yeah, no, I think that's good. I think I was unclear from reading the thesis. I thought maybe it was a mass balance. You were just perturbing a mass balance field from the present day fields. I'm not doing it when I use these corrections, but the other one I am just using the mass balance fields, which we did talk about might provide some errors due to we're not catching some nonlinear effects, for example with Albedo. Yes. But I did do a test of it, and it was, I think I added a slide with it actually. Let's see, if we're lucky. Temperature? Nope. There's something else. Yeah, this is when I just use the mass balance and anomalies and the energy balance anomalies. It's not really, this is just for the RCP 8.5 scenario. The first time slide, it was not really important, but then when we came to the larger one, I think it's a 30 centimeter difference, something like that, which over 300 years would be fairly significant, I guess.
10% level or something.
Yeah.
And that was really just my question: is does it matter, or how much of a difference is it? So.
Yeah, it matters a little, at least for these simulations.
Yeah, because it's not a linear mapping of the meteorological fields onto mass balance. So since you have all that information, it might be it might be the proper way.
Yeah.
Okay. And just I guess to conclude, some final questions about the ice dynamics modeling itself. It's another inherited model that you've done really well to get up and running, because it's not so simple. Can you tell us a bit about how PISM treats sliding at the base of that neocle?
Yes. Basically what it does is that it uses the shallow shelf approximation to calculate the sliding, and how much it slides is dependent on the how much water is at the surface, how much water is in the till, and then it basically assumes that there's a deformation of the till.
Okay.
Yeah.
How do you get the amount of water at in the subsurface?
Well, it calculates the amount of melt that percolates to the ice. So basically we do a spin-up, which has a constant climate spin-up. We calculate the amount of melt, and it's how much percolates down and comes. But in this model, if your ice cap is temperate, it's always going to be completely saturated for every point. So you're going to have sliding at every point.
So in that sense, you don't worry about the drainage itself. You just assume
no, you can add. They do have it takes a lot longer to run, but they do have something where you can add drainage, but it doesn't really affect the saturation of the till because they only start draining once the till is completely saturated, and it starts draining. So they really don't have any in between in this model, which I also had some problem with because as long as it's temperate, then it's going to be completely full till and start sliding. If it's not temperate, then it never slides. So there's not really any in between.
Okay. Oh no, that's good. I wasn't clear on that again. So it's possible to have maximum sliding everywhere.
Yes.
All times.
Yeah, it is.
And then do you use in separate grid cells, shallow shelf and shallow ice, or do you always superimpose the two?
It depends on the area. In some of the parts of the accumulation area, I only use shallow ice, and then in the depletion area, I use shallow shelf plus shallow ice.
Okay.
And I think maybe in 1 or 2 points at Breda Mayfield, I only use shallow shelf because it floats. But
right.
Yeah.
And then, but in most, it's
in most
combined.
points, it's a combination. Okay. Yes.
Would you be able to tell us the theoretical difference between the two models? In thinking of the stress balance of the ice, what does it mean, the shallow ice versus the shallow shelf? Do you know that?
Well, they're both shallow models, and one of them, they're both is simplification of the full Stokes model, and the shallow ice approximation is basically for a thin ice cap where the area is a lot larger than the height and has no sliding at the base, and how this does. So this is one extreme. And then there's the other extreme where we have an ice cap that's only floating, and the shallow shelf approximation then is used for that. Yeah. So we just have an ice shelf.
Do you know the stress balance, the sort of F equals MA for the ice sheet? Did you read through some of that or look at that?
Well, I mean, there's in the Stokes model, you assume there's no accelerating terms, so there's no F equals 0, basically.
Right.
Yeah.
And then the different F then has a few different components, the different stresses that act.
Yes.
So do you know within the shallow shelf, let's start, what stresses they're considering?
Yes, but I just have to remember which ones. It's the... Yes. I do know this, but right now I can't remember. Well, it's the... Well, one is the kind of forward deformation, the other one is vertical, but I forgot the name of the stresses right now.
It's okay, it's not core to your contribution at all, but it's the model.
I did write it in the thesis, I just don't remember right now.
It's the model you're using, so
yes.
it's good to kind of know what you're turning on and off with it. I think there's something fundamentally inconsistent in combining the shallow shelf and shallow ice for this at the same location.
Yeah.
Related to that stress balance, because the shallow ice assumes for the internal deformation, its main focus is the internal deformation, assumes that there's the full gravitational driving stress is at the base.
Ice column, yes.
Yeah. But if there's actually sliding, it should be much reduced basal drag.
Yes, that is true, which, I mean, most shallow models would not take that into account, though. Isn't it only the Stokes that knows the full difference between when there's deformation and basal drag?
Yeah, but you're calculating it, or within PISM, this is, again, it's not your model, you're inheriting this, but within PISM it is actually getting some estimate of that reduced stress, which would probably be more appropriate for the shallow ice part of it. So if you're continuing on with this, and maybe even for your third paper, I think it's worth to think about that a little bit.
Okay.
But I know that that's the way PISM's configured, but it's actually not honoring.
Wouldn't it be calculating the stress twice if I do an adjustment to the?
It has to be iterative solution.
Yeah. Okay. Yeah, that's true.
Yeah.
That would be.
But I think right now it's not honoring conservation of momentum when it's the way it's set up. So.
Also, I mean, for these simulations, there's such big errors in my mass balance that I really don't think this is going to make a big difference.
That was maybe my next question: is if it's what do you consider the biggest uncertainty in the future projections?
The estimates of the mass balance from the regional climate models.
Yeah.
I would say is the biggest.
Yeah, that's probably true.
Yeah. Yeah, I don't think there are also uncertainties in the ice flow model, but it's nowhere near as big as the mass balance.
In fact, that's why I've kind of moved over the last 15 years from the glacier modeling into a lot of the mass balance modeling, because I came to realize you can make the ice sheet do whatever you want depending on the climate you give it. And
yes, I
really
realized that too. If I just change how soft the ice is, I can either make it very big or I can make it disappear in 100 years. So it can be very variable.
I'd like to finish, if I can, with just a really open general question, which is to ask you, I guess, what you're most proud of. What do you feel like your biggest contributions are here?
I quite like the future projections with all the ice flow models. I'm quite happy with those, although they're not, of course, perfect. I think I use a lot of different models that have not been used before, and
I think you could pick any part of your thesis, but I think you're really set up to continue in this field if you choose, because you've gained a lot of familiarity with these different models. Not many people can work in that space as well as you've done. So in a bit more than 3 years, you've learned an awful lot. So congratulations.
Thank you.
Okay. Do you have any last questions? Okay.
So this concludes the examination of the candidate by the opponents. If anyone wants to ask questions or make comments, now it's the time to do so. Do you have any questions, comments? Except you guys, you are not allowed to do it. Any questions? Okay. So, ladies and gentlemen, we, meaning me and the two opponents, will now leave the room to consider the results of this examination. And you just wait. So could you just please follow me to the room that we can? Yeah. The two of you can just sit down. Or you can start if you want to, but I mean, you start. Okay. So the following text has been documented and signed into the PhD registry of the Faculty of Earth Sciences, University of Iceland. Doctorate from the Faculty of Earth Sciences, Louise Steffensen Schmidt, 26th of March 2019, I believe that's today. By resolution of the Faculty of Earth Sciences, Louise Steffensen Schmidt, dissertation, short and long-term model simulations of the evolution of the Vatnajökull ice cap Iceland has been approved for a doctoral defense in geophysics. The defense has been made, heard, and accepted. We therefore, this is the fun part, declare Louise Steffensen Schmidt a doctor in geophysics, Philosophia doctor from the University of Iceland. So, in confirmation of the award of the doctorate, I present this, all these documents. Okay, so this is your doctorate thing. It's in 3 languages. It's in Latin, it's in Icelandic, and English. I can read 2, and the 3rd one I don't understand. I'm sorry. Congratulations.
Thank you.
And this too, as well. This is from us.
Thank you.
Okay. So, would the opponents like to address the candidate? Do you want to say any words?
Just one thing.
Yes, Javier. I like that.
So I can do.
Yeah, you can be, or you.
Yes.
Yeah, you can. Yes.
I think it's okay. No, I just would like to congratulate for your PhD. I know that we are here for evaluating your previous work, but what about your future work? Do you have an idea for postdoc, or do you want to continue in research? Now it's finished. Yes. Okay. Mm-hmm.
And Sean, do you want to say something?
Yep, I won't try to recruit here, but maybe later. But I will just say congratulations. Again, you made our job very easy. It's such a pleasure to be here. Thank you.
Okay. So congratulations.
Thank you.
Welcome. Excellent. And if you, Louise, do you want to say something to the opponents or to the people here?
Well, thank you for coming, of course, and for approving this. And I think there will be a reception in Asker now, where there will be a little bit of food and drinks, so you should all head over there.
Okay.
If you're not going to say that, of course.
Me? Yeah, well, I can, yes. So in Asker, you all know where Asker is, I hope. It's just on the other side. It's not very windy at the moment, so
No, it should be
we
okay.
should be all fine. Okay, so before we take off, we always, the faculty always has something to give to the candidates, okay, as an appreciation. This is a fantastic book. We used to give flowers. I don't know if you remember that. This was not very practical, especially when people were leaving the country. To take flowers on the plane is often not allowed even. So we changed to fantastic books, okay? So, Louise, here is the gratitude from the faculty. So, congratulations again.
Thank you.
It's heavy.
Yes, I noticed.
Okay, so, And now I switch again to Icelandic. I'm supposed to do that. Að svo mæltu þakka ég öllum sem voru viðstaddir hér fyrir í dag og segi þessari athöfn slitið. So, thank you very much again. And now let's have a party. So please take all your things and belongings. And then there is a book outside that if you haven't written your name, please write your name. Maybe you guys didn't write your, did you write? No, it's like a registry. Okay, I'll have to do this. Excellent, well done.
You really did make it easy for us.
Yes, exactly.
It was very nice. You were very nice about your questions, so that's good.
Well, thank you very much. Thank you. So, congratulations again.
Yes. No, it was very nice. There was a lot of questions that I answered. It was very nice. Not that it was difficult, it was just very nice. This is very nice, yes. Yes.
Come back for it.
I still have funding until the end of the year. Yeah, exactly.
And then?
If you need recommendation letter for your postdoc, let me know. Yes. Because I think you need to continue research and perhaps in the Copenhagen team.
I would really like that.
Yes.
I actually totally agree. We need someone like you.
Yes.
I will probably take you up on that then.
Yes.
Svo að þetta nota sem stýringu fyrir... Já, það bara einhvers konar app sem stýrir þessu. Já, það velkomin hana. Það nýkomið, Ég sé nú að skjári sem notaður, ekki skjári sem... Það var skjár sem kom svona upp. Já. Hallaði örlítið. Þess að greinilega það búið að skipta honum út. Frá því í janúar. Þannig að... Ég finnst það líka vel hann var alltof beinn. Já, þegar þú stendur svona, Þetta ennþá í gangi. Alltof beinn. Já, það fyrirlestur beinan skjá. Já, svo hérna bara eitthvað system. Hér átt að gera eitthvað meira. En ég veit ekki hvað það þetta. Þetta búldósir. Það eru 3 búldósir hérna. 1, 2, 3 og það var dregið út í það allt sem þurfti. Það fer rörin frá þessu, við bæði á milli þeirra. Það var hérna, koma út hérna í hotnir hérna hinveginn við þetta. Sett. Já, þetta svona pakkur. Já, hérna tækja henni líka. Já. Og var hún þessa renni hérna. Já. Svo önnur tafla þarna uppi sem við gátum ekki skoða á það. Lokaði ytri hurðinni, þannig að það svona, þetta eiginlega svona frontur, kvikmyndafrontur. Stækka tjaldið. Ég veit ekki út af hverju þetta sem geta haft stærri mynd. Ég sé náttúrulega eins og þessi mynd geti verið miklu stærri. Jú, hún getur verið miklu stærri þessi. En einhvern veginn, ég veit ekki hvað það er sem gefur
það að þeir vilja stærra tjald og þá er að tala að hafa tjaldið hérna við þessa brún.
Já.
Og þetta tjald kippt upp og niður.
Já.
Sem bara þarna, skýringum.
Já.
Og það bara alveg rauð tengidósinni þarna í og það stillingar. Ef þetta verður gert þá verður aldrei innfellt tjald. Það ekki hægt. Ef það fer svona framlega þá fer það bara út í lampakassan og í alla festingar sem halda þessu drast uppi. Þannig að það verður alltaf utanvindi kassi. Þess að þið þurfum að gera í raun og veru það bara taka lögnir hana og hún verður þá alltaf bak við tjaldið og í tjaldbygginni og bara svona sem það, þá bara komið.
Já, mjögulega fyrst að það verður að breyta þessu og færa þetta svo framalega. Nei,
það verður bara, sko, þetta tjald verður bara rifið niður eða sett upp alveg upp og það verður bara kassi sem utan á tjaldið og verður bara snýða svona víða flottur framar á kassan. Það ekki hægt að fella það upp út af því að það komið svo utanlega að það fer í lampana sem eru hérna inni og alla festingar sem halda þessar panel uppi. Það eru bara teinar sem eru upp í lofti. Þú ferði bara í gegnum það strax. Þú getur ekkert fellt þetta uppi og ég held að menn sé búin að skilja það.
Og er þetta eitthvað sem er á restunni?
Já, þetta gæti smotli inn einhver tíman bara að það sett upp nýtt tjald. En það sjálfsagt ekkert mál. Þetta fer upp, rafmagn þarna í dósinni, það hægt að opna lampan ef þið viljið fara með rafmagn ofan á pallinu og í hérna tjaldið, skilur. Og það rafmagninu þarna bara, sko, þetta stýrt með daleiningum hérna uppi og það bara alveg að sama upp og niður. Þetta eru 4 vírar.
Hvað er dali hérna?
Það bara upp á sölu hérna.
Upp á sölu hérna?
Já, það tafla þar. Við bara komum lína á það.
Vel.
Svo hérna.
Já, nú það. Þetta ekkert alltaf svona.
Nei, það víslega stórborðin sem sett.
Já.
Eða mörg, þetta eftir, mér var nú svo fannir þessi hilla undir hérna, myndaðulega. Það fáránlega ljúf. Já, eitthvað. Hann var svona langa, bara hann var eins og þess að stutta. Myndast
Gekk þetta ekki bara... Já, ég bara endilega gerði það. Gekk þetta ekki bara vel hérna í dag?
Ég hef hundið það við þetta, en ekki tengdir var þetta Doktorsvörn.
Já. Er það ekki tengdir því?
Ég er með rafvirkjar húsins, sko.
Já, ég skil.
Og hann var nú svona að vera að gera breytingar og þetta er starfsmann sem var að koma til starfa. Og ég er eiginlega bara að segja honum söguna.
Ég skil.
Ég ætti eiginlega að halda fyrirlestur.
Já.
Bjóðu ykkur bara í salinn.
Já, já, já.
Já, þetta er bara flestum.
Það er bara...
Já, ég er ekki
Það er ekki hérna sem leist, þannig að þá get ég farið það.
Já, það var eitt vekkingur að fara á gólfinu.
Já.
Ég veit ekki, hann getur verið farið.
Akkurat.
Já, takk fyrir. Þannig að lýsingi hérna er Dali, þú getur slökkt hana, dimma hana og eitthvað leys. Ég þekki þetta Dali sem er rosalega lítið að þetta virkar. Ég bara, stjórnleikendar er alltaf upp í skáp og það er ofan að það við þýðnar. Hann er eiginlega til þess að Síra þessu, sko. Ég er bara ekki, fyrst er bara allt af, og svo bara, það var ekki gott, þetta sýttir hérna. Þetta er bara eitthvað svít. Og breytist það meira ljótt en þessum hérna. Það er svona ákveðin. Það er stemning svít, sko. Þetta er stemning.
Ég veit að pera svona skjávarpa getur kostað alveg morðfjár.
Það er að finna út í það, þá er bara að slegna þau.
Nei, þetta er bara hljóðið. Og, ég veit það ekki. Hvort það maður á að skipta sig að þessu?
Sjálfur sig ekki umsögum að rækka koma.
Já.
Og gerir það, það getur verið að sjá það upp einn. Við myndum að vera að setja í slökk og stofakunum þegar það er eitthvað örugglega kasting.
Já, ég er hópið það, já. Kannski ég er á þetta, ég veit það. Nei, þetta er eitthvað.